Hello, my friends. I'm going to teach you today, or in this presentation, I'm going to teach you a couple of right-hand rules. All right, we know one right-hand rule already to find the magnetic field around a straight current carrying wire. Okay, and that one said, remember, we have a wire that looks like this. Let's say that current's going this way. We put our right thumb in the direction of the current, and our fingers wrap around the wire in the direction of the magnetic field. So the magnetic field here would look like that, right? It comes, to use these symbols, comes like that on that side of the wire, goes like that into the page on that side of the wire. Behind the wire, it's going up to the left. In front of the wire, it's going down to the right. Hopefully that one is pretty comfortable by now. We're going to learn a couple today, really, I guess three, well, we'll call it 2.5 right-hand rules. This one here is about right-hand rules near a loop of current. And then we'll do one for like a bunch of loops of current. Okay, so the one for a loop of current, let's say that we hooked up a battery that had a positive terminal here and a negative terminal here, and we hooked this to there, and we hooked this to there. Hopefully you can tell what how this is supposed to be represented. This is a loop of wire that we're not looking like that. We took this and turned it so we get it, well, like you see here, okay? And if we hook up the terminals like you see, well, again, if we want to know the direction of current, we always want to talk about direction of conventional current or direction of free positive charge flow. That means current would go up here. It would be going, really current would be going away from us here, right? These are directions of current. And it would be going down the back, all right? These are all currents. Make sense? Okay? Well, what we can do is, well, we can either, follow the rule for straight wires, which would just say, in the front here, in the front, we could take our right thumb and put it in the direction of current, put it up, and our fingers would wrap, let's see, inside that loop, our fingers would wrap into the left. And outside the loop, they'd wrap to the right. And then we could do the same thing in the top. You'd have to put your thumb into the page. Inside the loop, again, our fingers would wrap to the left. And outside the loop, they'd wrap to the right. And the back, with thumb down, again, inside the loop, your fingers would wrap to the left. So everywhere that we do this, inside the loop, the magnetic field points to the left. Outside the loop, it bends back around and points to the right. We can use a different right-hand rule for this also. So again, if you're comfortable with the right-hand rule that we've done for straight current carrying wires, it works fine for coils. Whoops. But there's another, come on. Oh yeah, the other one is this. What we can end up doing is we can wrap, of course, your right fingers in the direction of conventional current. And two, what'll happen if we did that, our fingers, right fingers, would go up the front, down the back, and notice, because you're going to have your thumb, anytime we do these things, if we wrap how am I going to draw this? When you're looking at the back of your hand, knuckle, 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 fist. And there's your thumb, woohoo, there's your thumb pointed out that way. So we always, as opposed to having your thumb just dangling around, we stick that thumb nice and straight out. All right, so if you have your thumb pointed straight out, your thumb's pointing to the left. Remember, we said before that everywhere inside the loop, we said the field points to the left. So this means that your thumb points in the direction of magnetic field inside the loop. All right, so that means that our magnetic field, I'm going to just move this and this. Our magnetic field looks like this. Inside the loop, it points this way. There's B. And then that field goes back around like this, goes back around like that. looks like that. Now you notice that looks a lot like the field, I'll say B, near a bar magnet. Remember that? We had a bar magnet like this. Let's go north, south, and we said that the field lines pointed like this, and then they came back around like that. Yeah? So a loop of wire, a loop of current carrying wire, makes a magnetic field just like a bar magnet. Hopefully we can see the similarities. This would be, our north end. This would be our south end. Okay? Put this here. So, ding, ding, ding. What we talked about in the last video is we got to get to the point of why are things magnetic? Well, sure, we said that some things, right, in magnetic things, the magnetic domains are all lined up nice. And in non-magnetic things, the magnetic domains are all over the place. Well, these little domains, what are they? Well, here's the deal. Like we said, everything has the potential to be magnetic because everything has, I don't know, billions, trillions, zillions, whatever you want to put yuns in there. Everything has zillions of tiny little loops of current already. All these little tiny loops, what do you mean little tiny loops of current? Well, there aren't little wires and everything, but there are orbiting electrons in everything. Electrons are constantly whizzing around nuclei. And as long as in a magnetic material, all those little loops of electron current are all aligned the same way, what you get is that. We get magnetic domains made by tiny little loops of current that are all aligned in the same direction. And then things are magnetic. A piece of wood, right, has electron loops that are all over the place, doing all sorts of, in every orientation you can imagine. And then their magnetic domains are not aligned. But in a good piece of magnetic stuff, those electron orbits are all in the same plane. And therefore, all these little tiny, magnetic fields that look just like this all add up and give you a macroscopic overall magnetic field. Okay? Okay. Now, what we can do with this is we can, instead of having one loop of wire, you can make a whole coil of wire. This is called a solenoid. That popped up for some reason. But near a solenoid, well, we do this thing. Yeah, we look at, why did that come up first? It just comes up. Yeah, good. We can do this just like a single coil, where if we know the direction of conventional current, we wrap our fingers. Hey, come on. Our right fingers, of course, in the direction of conventional current. Your thumb will point in the direction of magnetic field inside the coil. Okay, so if we did, I don't know, let's define the fact that conventional current goes this way. Well, we can wrap our fingers up the front of this big coil, down the back, and our thumb points to the left. So that means inside the coil, the field looks like this. And points in like that, and then wraps itself back around here. And again, that means that this is our North Pole, and this is our South Pole. Okay? Now, again, so what? Well, if we put, not just air inside that coil, but if we put what we call a soft magnetic material, and this means something that can be made magnetic. Ding, ding, ding. Remind me to demonstrate. Remind me to demonstrate. Remind me to demonstrate. If we put a soft magnetic material, like an iron bar, iron's a soft magnetic material, inside that coil, what we get is a magnet that you can control the strength of. We get what's called an electromagnet. Okay, the iron by itself, not a magnet. But if we put it in the presence of a strong magnetic field, we can align its magnetic domains. It turns into a magnet. Well, how do we do that? We do that by turning on current. All right, and the more current we run, the stronger the magnetic field becomes, and the stronger magnet we get. All right, we'll demonstrate that as well. Demonstrate, demonstrate. Okay? Okay, a couple of examples for you. You. No, I'll do the first one. You do the second one. And third one. You. You. So, let's see. What's the direction of the magnetic field at the center of the solenoid? So, let's see. Positive here, negative here. That means we wrap our right fingers this way. That means my thumb is pointing into the page. So, B on the inside looks like that. Hard to draw, but B out here would, of course, wrap back around like yay. Good? What's the polarity of the battery? So let's say that we hook this bad boy up here at number 2. Let's do this. And you tell me if it's like this or like this that goes in this box. Which way is the battery aligned? Again, here are your options. Like this or like this, right? The long end being the positive end. Let's say that there's a let's say the magnetic field goes like this. And wraps back around like so. You tell me what direction the orientation of that battery. Duh. Sorry. Okay. Let's see. Oh yeah, sure. With this one, if we have defined there to be a north pole and a south pole, as you see, the question is, which way is current going right here at that point in the wire? Got it? Good. Next. Oh, here's where it starts to get awesome. Now, we start to talk about electromagnetic interactions and another right-hand rule, a big, powerful one. But the whole thing with electromagnetic interactions is we talk about what magnetic fields do to charges. Okay, so we got a field or two magnets like this. As you know, the magnetic field between a North Pole and a South Pole looks like that. You ought to draw your magnetic fields touching the magnets. I'm breaking a rule there. All right, that's a nice uniform field, a field of constant strength and direction. And the question is, if I put a positive charge right there, the question is, what'll it do? Think for a moment, maybe sketch down your answer. What happens to that charge? Ready, set, think. Pause. Pause. Okay, you're back. What does this thing do? Well, it does nothing. Nothing at all. Is that a surprise? I bet it is to some of you. I bet some of you wanted to say, it goes this way. Maybe, that's probably the worst thing we could say is it, quote unquote, goes. If you wanted to say it accelerates this way, I can see why you would say that, but it does not. Remember, magnets and charges are different things. North is not positive. North is north. South is not negative. South is south. They are not the same phenomena. So here's the real important word, stationary charge feels absolutely no effect from that magnetic field. None. Nothing happens. Yes. However, in a case like this, I reversed the direction of the field because I felt like it. Let's take a charge and move it through this field. Let's move it through this field. Watch and see what happens. We move this charge. No. Gee, it looks like nothing happened, right? No fun. I mean, yippee-doo animation. Come on. It looks like it slowed down or something, right? Well, yeah, it looks like nothing happened. Maybe it slowed down. But what if we take this same field and instead of looking at it like this, let's look at it from over here. This is your eyeball. Let's look at it from that way instead. And now, instead of us seeing the field pointing right to left, now we see the field going away from us down here. Okay, if we looked from over here, we'd see the field going away from us. That's what all these X's are. You know, it's this, just without the circle around it. Lots of times you'll just see the X, not with the circle around it. And here's what actually happens. Where before, up here, we didn't see anything happen to this charge. Here's what actually happened. Oh, yeah. It actually changes direction. All right? It changes direction. It actually moves in a somewhat of a circular path in there, but only while it's in the field. Notice when it comes out, believe me, this was a real pain in the butt, this animation. It's pretty, the motion out here, no change in direction. It's only a change in direction when it's in the field. It comes out of the field and it goes in a straight line again. Okay, but while it's in the field, that charge does feel a force. Okay? It does feel a force. So, next slide. This charge follows a path that looks like this. Okay? And at any instant, we can say that the charge, I don't know, was moving, well, this way, and was moving that way, and was moving that way. And the force on it points, well, let's say right here it was pushed, I'm sorry, it was moving still, too many colors. It was moving this way at the very beginning, and it was pushed at the beginning like this. And then it was pushed like that. And then it was pushed like this. And then it was pushed like that until it left the field. So there are forces. So we have three vectors now. Velocity, magnetic field, and force. And so what we can do is use our right hand to figure out or to relate the directions of these three vectors. All right, there's a vector for force, there's a vector for magnetic field, there's a vector for velocity. And so, well, in the right-hand rules we've used so far, we talk about curling our fingers. Here, we're going to do this. We're going to keep your right hand flat with your thumb finger, 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 thumb. I'm an artist. So you're going to, look at that thumb on that guy. You're going to have your hand just like that. That's disgusting to look at for some reason. You're going to have your hand like that. The important part is that your thumb is pointing straight out. Okay? And if you look at this, there's lots of different ways. There are actually three different ways that you could orient your hand so that things work out right. And you might even try to pause. Here's what I want you to do. Pause for a minute. Okay? And when you do, what I want you to think about is, how could it work? How can I make, this thing work? Well, if you just put your hand in a certain, in a certain orientation, you might be able to say, oh, look, if I put my hand like this, my thumb happens to point in the direction of this quantity, while my fingers are pointing in the direction of that quantity, and my palm actually now points. We might say here, pushes. All right? Like if you push with your palm, that points in a certain direction. You could push in a certain direction. All right, so see if you can figure out one way we can make these things work out. So pause and come back in a minute. Do it. Okay, so I bet a lot of you have come up with the fact that if you just put if you're looking at your computer or your phone or whatever you're looking at, if you just put your hand almost like on the paper, with your fingers towards the top of the paper or your fingers towards the top of the monitor, you'll notice that your fingers point in the direction of velocity, the velocity vector. I mean, let's look at this case right here. Right? Your fingers point towards the top of the screen. That's the direction of velocity. You'll notice that your thumb points in the direction of the force. And you'll notice that your palm pushes in the direction of magnetic field. Right? Velocity up, there's your fingers. Force to the left, there's your thumb. B into the page, there's the direction your palm pushes. So that's one way you can make this right-hand rule work. I prefer a different way because I can talk through it. All right. Notice also that I say if you put your thumb in the direction of velocity, that means thumb would be towards the top of your screen. Well, your fingers now, if your thumb's towards the top of the screen, you could actually point your fingers toward the screen, into the page. And if you do that, thumb up, fingers in, you notice that your palm points to the left. And if we look at this same point right here, you'll notice that your palm pushes in the direction of force. I like that one because here's how I say it. I say, if you're talking about your thumb in the direction of velocity, I say, hey man, I say, going my way, bro. If you're hitchhiking, going that way. Right, that's the worst one. Now, this one I can say that fingers, field, I say, fingers in the direction of the field. And then I say, here, I say, palm, push. Right? Because a force is a push. So that's how I remember it. All right? Hey, you going my way, bro? Yeah, and then the fingers feel and then palm push. So if we look at this location right here, right, we put our thumb this way, our right thumb that way, and we put our fingers into the page for the field, notice that your palm will push that way. So it works anywhere. All right? Now this part, charges pushed, well, it's always going to be this, perpendicular to both V and B. Good? That's what we call a right-hand rule for a charge moving in a magnetic field. Okay? Yep. Here are 6. I'll do 1, but 5 more for you. So you'll do you. If we look at this one here, well, I'm going to do, let's see, going my way, thumb, so this is going to be thumb down, fingers healed, in, and if we do that, thumb down, fingers in, palm pushes that way, and that means the force exerted on this charge would be to the right, at least, when the thing is right here, right? It would be pushed that way. And then it would start to do this sort of thing. It would move in a path like that. Got me? So, yeah, it really should say, well, if the thing were here moving in that direction, because if it's up there where you see it, it's not going to feel any force. But if it's in the field, moving down, it's going to be pushed that way. Okay? You fill in these blanks. There, and there. Tell me directions. Up, down, left, right, in, or out. Okay? Right hand rule. 24 minutes. Not bad. Yep. See you soon.